Good day. Today we're looking at a couple of topics that of course are related to each other. One is cross products, vector cross products, and the other is angular momentum, which is a new physics quantity. Start with a quick look at vector cross products, and I'm guessing that you have looked at these in pre-calc probably. But we'll do a quick review because it might be a while since you have looked at them. This is a way of multiplying vectors, I guess. It's a mathematical operation that you can do to two vectors. And this is how it works. If I have two vectors, and for right now I'm not going to worry about there being any particular physics quantities, I'll call vector A 6, has a magnitude of 6 newtons or meters or something. Right now this isn't going to have any meaning in terms of physics. This is just going to be dealing with how we find cross products of any two vectors. Okay, then now I have a second vector, vector B, which has a magnitude of 5, and B 6 is clearly in the positive x direction in a standard coordinate system, and B is at an angle, and clearly I can measure this angle and find out that it is a 53-degree angle. Is equal to its angle from the x-axis reference direction. So now I would call that angle theta, but I'm not going to get too finicky about that right now, because here's the basic dealio, and that is if I want to find the cross product of these two vectors, I would say, okay, what is A cross B? And I would use the vector symbols, and I'd say I want to find out what that is. Well, the cross product of two vectors is itself a vector. So I'll call that for the time being vector C, is what we get when we find the cross product of A cross B. And by definition, this is what we know about vector C. It has a magnitude, and the magnitude of the cross product, C, is equal to, notice the lack of vector symbols here, is equal to the magnitude of A times the magnitude of B times the sine of the angle between A and B. Drawn tail to tail. And the direction of vector C is found by applying the right-hand rule that I will go over with you in just a second. So let's find the magnitude of the cross product of these vectors first. So to do that, I need the magnitude of A, which is 6, and the magnitude of B, which is 5, and the sine of the angle between them drawn tail to tail. You can probably see right away that that's going to be 53 degrees. But I'm going to move vector A, which is a magnitude of 6, and I'm going to move vector B. I'm going to draw them tail to tail, and I notice that in fact this is a 53-degree angle drawn between the two vectors. So I will label that. This is now phi, because this is the angle between two vectors, and that's 53 degrees. Okay, so now I'm ready to find the magnitude of the cross product, and so I will do this over here on the left. C is equal to A, B sine phi, and that's equal to 6 times 5 times sine of 53 degrees, and I plug all those numbers into my calculator, and I get an answer of 30 times sine of 53, and I end up getting 24 is the magnitude of the cross product. Okay, the direction of the cross product, as specified, is found by using this right-hand rule, which I have a nice little picture of right here, because I can't very well show you the right-hand rule because you can't see me. And so I will describe this picture, and that is if you take, now this has vectors A and B drawn with a different perspective. They're meant to be sort of in a plane, like B is coming out of the board toward you, if you will. Here's the thing. We have to deal with 3 dimensions, and we have to deal with drawing 3 dimensions on a 2-dimensional board and on a 2-dimensional video, and so we have to try these 3-dimensional pictures. Because a very important point is that the direction of the cross product of these two vectors is perpendicular to the plane defined by vectors A and B. So in the case of our problem that we have here, the direction of the cross product will be either into or out of the chalkboard. It's perpendicular to the plane of the, I just called it a chalkboard, I'm so old. It is perpendicular to the plane of the board, of the screen, and it's either into or out of the board. And it's good to recognize that we can, before we start playing right-hand rule, that we are limiting ourselves to those two possibilities. Is the vector cross product for these two vectors into the board or out of the board? This is where the right-hand rule comes in. And what this picture is trying to show you is that if you take the fingers of your right hand and curl them, you kind of, and I'll show this to you in class in real life, but you curl them so that they hit A and then B. So you kind of are rotating your curled fingers around your thumb. I'm just grabbing this picture. And the fingers, first of all, hit A, and then they hit B, and they do so traveling through the smaller angle between them. Recognize in the picture that we have up here, what's the angle between A and B? Well, there's two of them, actually. There's 53 degrees, or if we go this way, it's 307 degrees. So there's always two angles between vectors. The rule for the right-hand rule is that you curl your fingers from A into B, going through the smaller angle, which in this case is 53 degrees. When you do that, your thumb points in the direction of the cross product. In the nifty diagram here that's on the board, that direction is toward the top of the page. With ours, where A and B are in the plane of the board, the direction of the cross product C, and right now I'm going to get rid of this 307 degree reference, the direction of the cross product C is going to be out of the board. So if you curl your fingers from A into B, that leaves your thumb pointing back into your face, if you will. And so the direction of C, which I will make this color, the direction of C is out of the board. There's two ways I can draw that. One is, and you learned this last year, one is a circle with a dot in it, because that implies a vector coming out of the page. That direction's out of the page. The other thing I can do is try to do some cool 3D perspective thing where I say, oh, here's my coordinate system with X, Y, and Z coming out of the board, and now my vectors were the A vector's like this, the B vector was like this. So you have to recognize this is in the XY plane. And so the C vector in this case, which I'm going to make green, is in the, I didn't make it green. Do that again, because it's so important to make it the right color, is in the positive Z direction. So I'm drawing this C vector is out of the board along the Z direction. Now I'm going to just mark that angle between A and B to try to make it look more like they're in the XY plane. All right. So that's the magnitude and the direction of the cross product. It's a vector operation that you can have fun with. So what does that have to do with physics? Well, in physics, there are a number of physics quantities which are vector cross products. We've actually already run into one, I'm going to say one right now, and that is torque. You know what they say, your torque is R cross F. We have been defining directions of these quantities in rotation, so I'm going to say a note right now about the directions of quantities. And we've been using clockwise and counterclockwise as the two directions. But that's nice, but that requires something to be the case, and that something is that everything is in the plane of the page that you're looking at, and everyone's looking at the page from the same perspective. And so this lacks a certain amount of sophistication, so we're not going to do that anymore, because we're going to be looking at situations where we have to recognize that space is three-dimensional, at least. So instead of using clockwise and counterclockwise, we're going to specify the directions for these the quantities we've been dealing with in rotation the following way. I'm actually going to skip angular displacement for right now, because angular displacement's a little bit of a bugaboo for reasons that you might be able to drag out of me if you're lucky. But we will look at angular velocity, the direction of angular acceleration, and then we're going to say a little something about torque. Okay, angular velocity, I will try to show this to you. If I have a disk in the plane of the board, there's the axis, and it's rotating counterclockwise, This disk has an angular velocity direction which is determined by another right-hand rule. And the basic rule, and again, this will be easier to show you in person, the basic rule is that if you curl your fingers of your right hand in the direction that this disk is rotating. So I'm going to say right now, take the similar to how we just did the last right-hand rule. This is so odd to try to do with this video, but to have your fingers curling along these arrows, if you have your fingers actually rotate your hand, your thumb should be pointing out of the board again. And if it is, that's good. So the direction of the angular velocity vector for this rotating disk is out of the page. And that direction is always along an axis of rotation. The axis of rotation of this rotating disk goes in and out of the board, and in this case, the defined direction of the angular velocity is out of the page. The direction of angular acceleration then follows, because this is defined as d omega dt, and so this is a vector equation. And so if you have something whose angular velocity is changing, then you find the direction of the change in omega vector, which is a matter of subtracting a final minus initial omega vector. For right now, I will say this: if a lot of situations are served by the following. If this disk is speeding or slowing its rotation, we end up with a rule very much like plain old acceleration, and that is this: if omega is increasing, then the angular acceleration is in the same direction as the direction of omega. And contrarily, if the angular velocity is decreasing, then the direction of the angular acceleration is in the opposite direction of the angular velocity vector. Okie doke. Then we want to say something about torque. See, and we've been defining torques as clockwise and counterclockwise, but in fact, the direction of a torque actually has a more rigorous definition, because formally, torque is actually a cross product of R cross F, these two vectors, meaning the following: if you have a pulley and you have a rope that's pulling on the pulley, there's a mass hanging off of this pulley, and I might say, oh, the tension force, so if I draw a free body diagram of this pulley, it's going to be remarkably similar to the sketch I already have, except I'm going to draw, instead of a rope, I'm going to draw the tension force, and I say, oh my goodness, does that tension force create a torque? Remember, torque is always relative to an axis, and that axis is in the center of rotation of this pulley, because this R vector up here is a vector drawn from the axis to the point of application. Good notes here, going everywhere. Point of application of this force. And so in this case, that vector, the R vector, is going to go from the axis of rotation to the point of application of that tension force. That's R. Okie doke. The definition of torque then is that it is R cross F, meaning if I take this R and the force, tension, and draw them tail to tail, then the smaller angle between them, which happens to be 90 degrees, that's phi is 90 degrees, allows me to find the direction of the cross product of these two vectors. So I would ask you to try to find the direction of the cross product of R cross T, and using the right-hand rule we learned at the beginning of this lesson. And you should find, in this case, that the torque is into the page, away from you. When you cross R into T with your right fingers, your thumb should point into the page, into the board, into the screen. And that's the direction of the torque. So torque is officially a cross product. And you know that the formula for torque that we learned earlier is R times F times sine phi. Now I'm saying it's R cross F. Well, golly gee, it's really the same thing, because a cross product, we find the magnitude by multiplying the magnitude of one vector times the magnitude of the second times sine of the angle between them. And that's exactly what we did earlier for our definition of torque in the Latin chapter 9 was torque is R F sine phi. This still is the correct value, the correct formula for the magnitude of the torque. To find the direction, we just apply that right-hand rule, and that's, as I say, a little more sophisticated than saying clockwise or counterclockwise. That torque created by the tension in this pulley is into the page. One other thing I want to say about cross products before we move on is that cross product, it looks like multiplication, but it doesn't follow the rules of plain old multiplication, meaning that it's important that we write torque as R cross F, because it is not the same as F cross R. Cross multiplication, cross product is not commutative. It matters whether you do one times the other times the first. You can't just switch them back and forth. In fact, if you try some right-hand rule stuff, you should find that if I take any two vectors, A cross B, and if I instead do B cross A, I should find that that new cross product is actually in the opposite direction of A cross B. So in fact, this is a statement of truth that the cross product of two vectors is the negative of the cross product of them switched the other way around. That was sophisticated. So do be careful, R cross F for torque, not F cross R, which is why the famous line is, your torque is R cross F.